This IIT JEE 2025 question on electrostatics looks complicated until you notice the trick, which is what many students missed. In the next few minutes, I'll give you the concepts and the shortcut tricks you need to solve this question smartly like an IITian would. Let's jump right in. Alright, let's read the question carefully. It says that there are two coaxial conducting cylinders, same length, radii root 2r and 2r. There are charges on the inner cylinder, which is Q on this inner cylinder over here. Outer cylinder is grounded, as you see over here. Annular region between the cylinders is filled with a material of dielectric constant, which is 5. Okay, so there is some region between the cylinders, which you also see in the cross-sectional area from the top. So this particular area, the shaded area, that has the dielectric constant. Now consider an imaginary plane of length L, which is the same length as that of the cylinders, at a distance r. So you see in the figure 2, this is the plane L. From the top view, the distance from the center is r. This is parallel to the axis of the cylinders. So you see in this figure 1 that this entire plane is parallel to the axis of the cylinders. Cross-sectional view of this arrangement is shown. We have already seen that ignoring these edge effects, we have to calculate the flux of the electric field through the plane. Now let's try to pause here and visualize the problem for key concepts. This is where many students would start thinking like, okay, this is a problem where there's an electric field, there is a complicated shape with a plane cutting through it, and then for calculating the flux, let's just calculate the integral of E dot ds, and then we see how we can vary the angles to cover the planes from one particular point to the other. That is one way, but it's going to take a long time, and this problem is not about long calculations. What you need to realize is how to break this down into simpler parts using Gauss's theorem. If you see at the bottom left, I have this handy diagram going on. You need to find the flux through the vertical plane cutting through these coaxial cylinders, right? Now we know that Gauss's law says that the flux is either integral of E dot ds or it is equal to charge enclosed by epsilon naught, right? So essentially what we want to do is we could take a Gaussian surface which is kind of encompassing this entire vertical plane and then try to see what is the charge enclosed by this system within that. Or we could do the integration route, which is going to be complicated. So let's just say that if we were to take a Gaussian surface, then we can calculate the electric field much faster. However, we need to be very careful about how to take that Gaussian surface. So before doing that, let's visualize how the charges are distributed over here to go step by step. So it is already known that the charge on the inner surface is Q, and these are conducting cylinders, right? So we know that those charges are going to get distributed on the surface of the cylinder, right? And those will be Q. Because this is a conducting cylinder, the outside one as well, so we know that there is a negative charge which is going to get induced on the inner surface of the outer cylinder. Also, there will be a net positive charge which will get pushed out to the outer surface of the cylinder, probably here. However, given that this entire setup is grounded, you would notice that these charges will go to 0 because all of these charges appearing on the outside is going to flow to the ground. So the final charge distribution we are left with is that there is positive charges on the outer surface of the inner cylinder and negative charges on the inner surface of the outer cylinder, here and here. Now we know the charge distribution of the system. Okay. Now given this system, this is a hollow cylinder. We know that the electric field inside the hollow cylinder is also 0. So E equal to 0 over here in this internal region, and then it is grounded outside. There is no electric field outside as well. So essentially we see that for the plane cutting through this entire setup, this particular region, let me switch to red, and this particular region is not under any electric field because these are outside. So those go to 0. There is no flux because of that region of the plane. If you notice the section of the plane which is inside this setup over here, the electric field here is 0 as well, because that's what we know. Inside a conducting cylinder there is no electric field, so there could be no flux that is coming from here. Again, if the electric field is 0, then the flux is 0, right? So these area of the plane. Let me just erase that out. There is no contribution to flux because of these external areas. So essentially you would see that the part of the plane which is this and this is having some flux. With that visualization in place, let's now proceed to step-by-step problem solving. Okay, now we know that the flux through this plane is occurring only due to the sections AB and CD, which we see in green over here. Okay, so if we were to calculate the flux through the plane, how do we take a Gaussian surface? And here's the trick that I was referring to. So basically, we need to find a Gaussian surface where the flux through that Gaussian surface is going to be exactly equal to the flux through these sections CD and AB, correct? Now, to be able to draw that Gaussian surface, let's see how we can take that. The Gaussian surface is right over here going through A and B. It is right inside this orange line, and then it goes through the sections C and D, and then from D onwards it starts very marginally outside this line and meets at the point A. Okay, if we take that as the Gaussian surface, what happens is that the electric field on this particular Gaussian surface is again happening due to there are sections AB, the curved section BC, the vertical section CD, and then the curved section DA, right? So let me just write down the flux would be AB, flux of BC, flux of CD, and flux of DA, right? And we know that through this surface, the electric field for this particular line outside AD and then BC is 0, so there are no flux contributions over there, right? So BC and then AD, they all go to 0. Okay, so eventually what happens is through this surface the flux only remains on AB and CD. Now you may notice in the question that they have asked us to ignore the edge effects. So one might say that okay, for this particular section here, because the Gaussian surface is kind of tilting away from this corner and going marginally outside this orange line, there might be some edge effects, but we are asked to ignore any such effects. So we can simply calculate this entire flux by taking this Gaussian surface. Now let's proceed to step-by-step problem solving. Here what happens is that we are going to take the flux through this region, which means that we need to find the charge enclosed in these regions, right? So if we were to look at this problem again, here let me switch to some other color. So if you look at this point OC and then this particular area, then we know that this distance is r, this distance is root 2r, which means this particular angle would be 45 degree, right? Because we know cos theta r by root 2r 1 by root 2, which is 45 degrees. Okay, which means that the charge on the surface BC can be calculated, because now we know that this particular angle, entire angle, if we join it, would become 90 degrees, right? Which means that this is representing 1/4. 90 degree out of 360 degrees is 1/4. So the charge here, because it is uniformly distributed on the surface, so it is going to be plus q by 4. Similarly, if you look at the bigger triangle, let me now switch to some other color, maybe yellow. You join the line OD and you take this yellow triangle, which is again, we know the extent, this particular hypotenuse is 2r, the base is r, which means that the cos theta will be 60 degrees, right? So this particular angle will be 60 degrees. Now if we again look at the total section, if we join this over here, this entire angle would be 120 degrees, which means it is representing 1/3 of that circle. So the charge outside will be this total divided by 3, which is the charge on the AD surface is simply given by minus q by 3. Okay, so in this Gaussian surface, which is A, B, C, D, this entire surface, and again remember that this surface is not just in 2D, it is extending above and below the plane of the paper, right? So in this surface, the total charge is simply q by 4 minus q by 3, right, which is minus q by 12. And now with the Gaussian theorem, we can simply say that flux is charge enclosed by epsilon naught, which is here talking about the magnitude. Then we can say that this is q by 12 epsilon naught. However, there is one last trick in this question where it says that there is a dielectric constant, which implies that this epsilon naught will become k times epsilon naught. And if you put the value of k as 5, the total flux would become 12 times 5 times epsilon naught, which is 60, which becomes option number C over here, which is the answer. So you noticed how there are multiple tricks that are involved in this question. First, we had to visualize the charge distribution correctly, then realize what sections of the plane are actually facing some electric flux. Then how do we smartly think of a Gaussian surface which can help us find the electric flux through that parts of the plane. Once we do that, then we use the Gauss's theorem to calculate the total charge enclosed and get the answer very quickly. That's it for this video. Let me know down in the comments below if you have any questions or if you would like me to cover a given problem. Keep working on your concepts and I'll see you in the next one. Thanks for watching. Bye-bye.